Good morning, good afternoon, and good evening to all of our attendees joining us today for this latest Data Science Central webinar. This is Bill Voorhees, your host. I'm the editorial director with Data Science Central and also chief data scientist for Data Magnum. So I'd like to start off our event today by thanking Figure 8 for sponsoring today's event. Figure 8's a longtime supporter of the Data Science Central community, and we're honored to have them sponsoring our event today. Now today's webinar is entitled AI Models and Active Learning, and that'll be presented by Figure 8. But before we begin, I'd like to briefly review the format for today's webinar. Today's event will be an hour long. We have one presenter, who I'll introduce in just a minute. There'll be 10 to 15 minutes of Q&A following the presentation, and today's event is being recorded and will be available on datasciencecentral.com later this afternoon following today's live event. So I'd also like to encourage our attendees to provide questions throughout the presentation, as we'll be reviewing and presenting them on your behalf during the Q&A portion of today's event. Well, I'm very pleased to introduce today's speaker, Jennifer Prendke, with Figure 8. Jennifer is Vice President of Machine Learning at Figure 8. She's particularly skilled at building and scaling high-performance machine learning teams and is known for enjoying a good challenge. Now, Jennifer trained as a particle physicist and likes to use her analytical mind not only for building complex models, but also as part of her leadership philosophy. She also takes great pleasure in addressing both technical and non-technical audiences at conferences and seminars, and is passionate about attracting more women to careers in STEM. So Jennifer, thank you for being with us today. We're looking forward to your presentation. Now, the increased availability of computer resources and the prevalence of high-quality training data combined with smart learning schemas has resulted in a rise in successful AI deployments. However, many organizations simply have too much data, posing a challenge for data scientists. Unless at least some of that data is labeled, it's essentially useless for any machine learning approach that relies on supervised or semi-supervised learning. So which data needs to be labeled? How much of a data set needs to be labeled for an ML application to be viable? And how can we solve the problem of having more data than we can reasonably analyze? Well, one promising answer is active learning. Now, active learning is unique in that it can both solve this data labeling crisis and train models to be more accurate with less data overall. In today's Data Science Central webinar, we'll discover the pros and cons of active learning as an approach, 3 major categories of active learning, how your active learner should decide which rows need labeling, how to obtain those labels, and how to tell if active learning is appropriate for your ML project. So Jennifer, with that, I'm going to turn it over to you. You can begin just as soon as you're ready to go.
Thank you, Bill. So it's my absolute pleasure to be there today. And so as Bill mentioned, today we'll be discussing active learning and more specifically the reason why active learning is the smart way to do data labeling and why it is the future of data annotation. So I think Bill has given a good introduction of myself, but I'll just go back to some specifics so that you have more context of where some of the elements you're going to hear today are coming from. So I'm, beyond my position at Figure 8, I'm also part of the expert network at the International Institute for Analytics, which means that I advise lots of companies on how they are working with their data, and I obviously specialize on advising them on getting the right training data. I was previously chief data scientist for Atlassian, and I manage large and smaller teams, and every single place I've been at, training data is a critical part of building machine learning models. This is why I eventually decided to join Figure 8. And so one of the really fun facts and one of the reasons I'm really a strong believer in active learning is that I ended up running the human evaluation team within Walmart Labs when I was working there as part of their research team. And so the human evaluation team is actually the team that's responsible for providing training data for the entire organization. And so I quickly saw that one major bottleneck was getting high-quality training data in sufficiently large volumes, because training data or labeling training data specifically is not cheap. And so back to when I was working over there, I saw that this was a problem, and I started trying to look for specific solutions. So now a little bit more about Figure 8. So Figure 8 is, as you heard before, a company specialized in providing high-quality training data and providing labels for training data. And so our mission is to empower data scientists to train, test, and tune machine learning for a human world. So our mission is really to help people make machine learning work in the real world, and that starts by getting the right data. So before we go any further, I would like to go through like a quick poll here because it's going to be helpful for me to understand what kind of audience we have here. So the first question here is going to be like, what is your primary job role, right? I mean, so are you a practitioner, a product manager, an engineer, or like someone who's just like trying to inform themselves? I'll just give a few more seconds for people to answer here. And yeah, I mean, so it seems that a lot of the people online right now are machine learning specialists and data scientists. So it's actually pretty good because we're going to be able to go in the technical depth, and I'm hoping for interesting technical questions at the end. I also see that there is some people from like the product management, program management side. So this is going to be super helpful as well for these people to hear a little bit more about like how you should move forward to enable your teams to have the right data and the right process in place. Next question was going to be like, so how advanced is your organization regarding machine learning? Are you just getting started? Are you already using extensively? Are you part of the very few lucky companies that actually already have machine learning models in production? And so I leave a couple more seconds for people to answer here. And yeah, I mean, so it looks like a lot of the people over there are already using machine learning extensively. So hopefully you'll find the talk useful, and you'll be able to make your machine learning models work even better after the end of this talk. All right, so this is our agenda for today. So today I mean, obviously active learning is a very wide topic, so we're not necessarily gonna go through everything, but I'm hoping that this is gonna give you a solid foundation to maybe move a little bit deeper into the topic and like start exploring the area. So before we go into active learning, I will explain and go over again like why is big data so important for machine learning, and then we'll discuss the challenge of like obtaining high-scale label data, and then we'll go through an active learning tutorial and go a little bit deeper through like different what you call querying strategies for active learning and approaches and so forth and so on. So let's get started. So let's talk about big data and machine learning and how big data enables machine learning processes. So I think it's fair to say that nowadays we live in a world of infinite data, or it almost seems that way, right? I mean, so compared to maybe 10 years ago when it was a challenge for data scientists to get the right training data, we kind of have the opposite problem right now, and it's actually making machine learning scientists really happy. So why is that? So first, if you look at the typical chart of like the growth in data, you can see that it grows really quickly, and so this is really helpful because it's empowering us to do more. And my favorite statistic when I share this type of charts is like really if you look at a specific period of like 18 months or something like this, you can see that it's growing like typically really fast. So if you look like a period of like 18 months, you will typically have like an increase in data that's almost doubling every 18 months to 2 years. And so for me, this is essentially means that 18 months to 2 years from now, we're going to generate just as much data as the rest of humankind before us. And this is simply mind-boggling when you look at things through that lens. And so why do we see such an explosion in data? Just to give you like an idea, is like so much is happening over the internet in every single minute, and so I'm sure you've seen this type of charts before. Like content is being shared like through Google, through YouTube, Facebook, social media in general, and so basically it keeps accelerating and accelerating. So let's go a little bit further actually. So why is it happening now that we are seeing such an explosion in data? So I mean, this has obviously something to do with the beginning of the digital age. I mean, it's not that we have suddenly become more interesting as a species, right? And so if you try to look into depth, like why do we see such an explosion, I think there are actually three main reasons why we're seeing this today, right? I mean, so number one, there is a huge surge in an explosion of new data formats. So if you think back like 10 years ago, like most of the data was textual, right? I mean, so content you would see on websites were mostly text, right? I mean, so back then, like beginning of the social media age, you didn't have that much like content related to like images, video, but like ever since then, oh my, we've seen like such an explosion of like sensor data, audio data, video data, image data, and so forth and so on, which is actually much more heavy and it takes much more space and more storage than text. And so that's one of the reasons why we see such an explosion of data these days. Okay, so another reason to me is like we also have like lots of new technologies. So we mentioned social media before. That's just one of the many technologies that are actually empowering us to not only generate more data, but also share more data, right? I mean, so there are more and more solutions for data storage. Data transfer becomes easier, safer, faster. With the IoT, we also have this opportunity to generate data at a personal level, which didn't happen before. So now if you have like a device like a Fitbit, or your cell phone or whatever, it's actually constantly recording everything that you as a person are doing, by opposition to 10 years ago when most of the data that was generated at a company level, right? And so this is like explaining like it's one of the reasons for such an explosion of data. And then finally, the last reason that I think a lot of people are missing is actually there is a lot of data duplication happening these days. And so just to give you an example, right? I mean, if you go to Google and you actually enter a search query over there, here you have an example of like me looking for the installation of a matplotlib. You're actually going to have like this page that looks like you have lots of similar documents. And if you open these different pages, you actually have exactly the same content with the exception of like the version number. And so you also have situations where people retweet things, they keep sharing the same picture over and over again, and so sometimes more data doesn't necessarily mean more information. And so that's one of the problems that we're seeing today. And so this is where you start seeing that big data is indeed an opportunity, but it's also becoming a problem that data scientists have to deal with because now they have too much data to work with. So before we move on to the next session, and the last thing I would like to mention is like I really would like to make a proof of concept of how labeled data is actually empowering us to do more cool things today, right? I mean, so for that I'm going to use the example of the rise of computer vision. So most people don't know that, but computer vision, actually, all the research in computer vision actually started like pretty much like 50, 60 years ago when like over the course of a summer, it was almost a challenge among academics that they were going to be able to solve the problem of computer vision within one summer. And so a couple of universities basically like considered that they were going to hire a couple of students and interns, and basically by the end of the summer, they would have a machine able to understand images better than humans. And so obviously it didn't happen because that was back in the 60s, and so it took a really, really long time until we reached the point where we actually have like real life machine learning applications that use computer vision. So what happened there, right? And so if you look at the whole history here, right? I mean, so some things started unfolding starting the beginning of the 2010s, right? I mean, so by 2011, like we started seeing like the ImageNet challenge where people started like creating solutions where trying to do like image classification. And so by 2014, 2015, we reached the point where these algorithms could actually outperform humans. And so this is quite remarkable, but this is like many, many years after the beginning of computer vision. So the question is, why did that happen at this specific point in time? And so my opinion is that this is all coming from the fact that there was a release of a brand new data set, really large data set called ImageNet that I'm sure a lot of people on the line right now know. It's actually a data set that contains like 14 million labeled images split across 20,000 categories. And this data set has become become the default for people to use when they're trying to work with computer vision. And so ever since this data set became available, and it's actually an open source data set, so really anyone can use it, every single either company or university out there started using that as the golden set for computer vision. And ever since then, you actually see that there is a dramatic change in what people are able to do with computer vision. So the proof of concept here is really until there was a large training data set that people could use to actually train models, paired with the appearance of technologies like GPUs and brand new models. Now we're able to use computer vision for daily applications. So now you see the importance of training data to get anywhere in machine learning. All right, so now let's talk about the challenge of getting consistent and large-scale data sets that are labeled. So I usually like to refer to this whole problem as being the big data labeling crisis. A couple of years ago, the challenge was to get sufficiently enough data to run and train our applications. Today, the problem has been transition to labeling. Because at the end of the day, if you have lots of data, you cannot really use them in a supervised way unless you have that data labeled. And so when it comes to labeling, lots of companies have either budget or time constraints. And so basically scaling labeling is becoming a real problem. So you have two ways to solve this. Either you want to label your data set faster and cheaper. So this is when you're going to use a machine learning plus human in the loop approach to label your data, right? I mean, so instead of having manual labeling happening and crowds of people, humans actually sitting behind their desks and putting bounding boxes around items on an image, you can actually have a machine learning algorithm do that for them, and then you use the human to validate, right? Or you can choose to do smart labeling, and smart labeling is really choosing what you want to label and what data is important to label. And this is where active learning can help. So let's talk about labeling through machine learning, right? I mean, so the example you see on your screen right now is actually the explanation of how one of the products that Figure It carries a video annotation is basically working. So just to give you an example, right? I mean, the typical video has 30 frames per second, so that's a lot of images you have to process, right? And so, so if you have to do everything manually, you can imagine how slow that process would be, right? So if you look at the scene you have on the picture right now, you have about 20 to 30 cars on that picture, times 10 seconds of video times 30 frames per second. And if you put everything back together, that would mean that if you find people who can annotate with a speed of 1 box per second, that would take them almost 2 hours to label these 10 seconds. And when you talk about the data that you want to use for training self-driving software, for instance, it's not 10 seconds that you need, it's tens of thousands of hours. And so you can imagine the amount of labor that would go into that. So basically the solution that we created is using object detectors YOLO, SSD, RCNN, and basically you would automatically try to predict the position of different items or objects on the first image, and then you would use a tracking algorithm to try to identify if where these objects are moving essentially across the different frames. So I mean, video lends itself very nicely to automate labeling, but because none of these object detectors are actually 100% accurate, you still want to use a human in the loop approach to actually make sure that the problematic bounding boxes are still being fixed by a human in case you get it wrong. Because at the end of the day, if you're going to use training data for building a self-driving software, you better have a really high accuracy in the data you're going to use. But then we've talked about the problem that comes with labeling large amounts of data and why machine learning can be helpful in that specific situation. But the problem of labeling is that sometimes even single annotations can be really problematic or really challenging to obtain. Why? So first of all, it can be hard to obtain. Sometimes annotating data row doesn't necessarily translate into putting a bounding box around an item on an object on an image. Sometimes it means that you need to run complex medical tests for a patient. And so that makes it challenging to actually even collect a single instance. Then it can also be expensive, right? I mean, so sometimes it can be like really complicated, because if you're trying to predict like the presence of oil in the ground somewhere, actually getting a label would mean that you have to dig a hole and figure out if you actually have oil in there. And so that you can imagine how expensive that would be if you really had to obtain like a significant amount of training data coming from that way. Then it can be really time consuming. So the example of like bounding boxes is actually pretty nice, because it's pretty straightforward and it's fairly fast to do. But like sometimes labeling consists in like identifying the topics of a very long legal document. And so this is actually pretty hard to automate, and machine learning doesn't necessarily help, or at least we're not there yet. And if you actually you need to have like a human, sometimes even a legal person, if that's a legal document, read through everything, and that can be both time consuming and really expensive. And then finally, the last thing is like it can be dangerous, right? I mean, so the example that lots of people like to use here is like, what about like you're trying to predict the presence of landmines in the ground, and then you have to make sure that your model was actually accurate, or you need to collect training data for building such a model. All right, so now that we know that it is complicated to get training data specifically at scale, let's discuss what the promises of semi-supervised learning bring, right? So I'm sure everybody knows supervised learning, specifically knowing that there are a lot of technical people on the line right now. Basically, supervised learning is any type of learning algorithm that uses labeled data. For instance, here you have this bucket of like vehicles. You know which one of them is a truck and which one of them is a car. And so that allows you to build an algorithm that can actually predict on new data if this specific data point represents a car or represents a truck. But then on the other end of the spectrum, you also have unsupervised learning. So unsupervised learning is like basically leveraging the same data before it is labeled, right? I mean, so the most straightforward example of unsupervised learning would be clustering, for instance. So you would still be able to differentiate the trucks from the cars, but you would not be able to name the cars, and you wouldn't be able to say that this specific type of vehicle is actually called a car, right? I mean, so labeling is really about like let's say you put like some human intelligence into the process, right? I mean, so now the machine understands that this type of object is called a car. And so people tend to forget that there is actually a sweet spot in the middle called semi-supervised learning that consists in like taking the best of both worlds and try to leverage the data that is labeled, but you don't necessarily need to have all of your data labeled. And this is like one of the examples of semi-supervised learning is active learning. So why is this important, right? I mean, so I think like we as data scientists have been trained to think about like getting our data, prepping our data, including labeling our data, and then we throw all our data at our models, right? And this is really what supervised learning is. But there is actually no reason why we should do and we should proceed that way, right? I mean, you could actually decide that you're going to be smart about what you decide to label and actually decide dynamically what needs to be labeled, right? So you have different ways you can do that. You can actually like decide what data you want to label prior to training. So you would actually prioritize your data when you send data to be labeled to a company like us. You could do that while you're training your model, so that's more of the line of active learning. And you could also decide to do that after training. How would you do that after training? You would basically label a small part of your data, and then basically use like decide to have like humans override the decisions of your machine when you believe that the predictions are not accurate enough or you're not confident enough about the predictions. So really, when you think about like supervised learning, right? I mean, so it's essentially like I think we're essentially doing machine learning the old way. The old way was about like collecting data, and then after you get your data, you actually decide to build your model. So you were in this mode where you would build data sets even before we knew what we were going to do with that. With the new order where big data is available and is becoming cheaper and cheaper to collect data, there is a brand new opportunity for us to think about getting our data and labeling our data, preparing our data at the same time that we're preparing our model. And this is really the value proposition here. All right, so let's dig into like active learning specifically. So I mean, I have a little tutorial here I'm going to share with you, but before we get there, I just wanted to give you active learning on a nutshell. So active learning is actually pretty straightforward to understand. So you start with an unlabeled training set that basically consists of all the data that you have at hand here. And you're basically trying to select data that you think would be interesting for you to consider here, right? I mean, so the first time you're going to identify your initial training set, the initial data you're going to sample, you're going to label first. It is kind of challenging because you don't have a lot of information about this data because, again, you have no labels to start with. But then you would start identifying, like, basically doing some kind of like smart sampling here. And then you would label this part of the data, and then you would recursively keep adding more and more data until you reach a specific point in your training set, and you end up with a finalized version of a training set that you think is good enough for you to work with. So when you think about active learning, I think it's really important to think in terms of learning curves, because this is really like giving you an idea of what the value proposition of active learning is. And so if you look at the gray curve on the right here, it's actually the type of learning curve you would expect in the case where you would be doing like a supervised learning iterations, right? I mean, so basically what I'm representing here is like the amount of labeled data over there comes as a percentage, right? I mean, so I'm assuming that this is the percentage of data I'm actually labeling and using to train my model progressively, right? I mean, so obviously we all know that the more data you have, the more accurate your model is going to become. This is why we all want to use more data when we are training models, right? But the real opportunity with active learning is like identifying a way to make that learning curve look better. So basically have this like nice, very vertical slope at the beginning where you would reach a fairly high accuracy much, much faster, right? And so the way you would actually do that is like instead of like progressively adding more and more data within your model in a random way, by doing random sampling, now you want to do smart sampling and try to be smart about the extra data you're going to add into your training set as you retrain your model over and over again. So active learning is really about like getting better learning curves. It's about like starting with having a higher starting slope so that you can get to a much better accuracy with a very minimum amount of data. And it's about faster convergence as well, right? I mean, so it's basically like reaching like a high, like the highest accuracy much faster. Just to give you an idea, examples of like research out there, like it's not uncommon to see people reach the same accuracy within like 1% of like the accuracy you would have with like the entire data set using only 10 to 15% of the data. Obviously, it depends on the applications you're going with, but this is really like the compression factor we're talking about here. All right, so how does it all work, right? I mean, so I think like I actually have like this step-by-step tutorial that I think is going to be super helpful for you to understand something called like pooling active learning. So again, you start with your unlabeled data set here. And then you're going to identify an initial sample, hopefully in a smart way. The way you could do that is like using some kind of like a smart sampling just in the same way that you would do for reinforcement learning. There are different techniques to go by that. You can also default back to like random sampling because at the beginning, again, you don't have a lot of information about your data. And then you would decide to send that data to a human oracle. You also have an opportunity to send that to a machine learning oracle. So the term oracle here is being used as the agent that provides labels for the data you're sending to it. And then what's going to happen next is like now you have your labeled data, you know that the image is like represents like 2 cats and 1 mouse here. So you have a small labeled training set, not a lot of data to work with, but it's fair enough for you to get started, right? I mean, so now you have at least some information about your data. So now you have this small data set that you can use to train the first pass on your model, right? I mean, so your learning agent here is like any kind of model you can think of, right? I mean, so the nice thing about active learning is like you can really use active learning in combination with any kind of models, right? And so you would start with your mini data set here, and you would train your model. And so obviously your model is not going to have a really high accuracy. Here, as you can see on my screen, like I put like 60% accuracy. Sometimes it's just going to be 30% accuracy, right? And then, but now you have a model that's probably going to be not so good for you to work with, but it's a starting point, and you have some label data that you're going to set on the site right for now, right? So now what happens next? So now that you have your model, you're going to use this model to infer the labels on the remaining of the data, right? Because now you have a model that can predict what images represent cats, what images represent mouse or another type of animal, right? And so obviously you can expect that the inferred labels that you can consider as a synthetic label, they're not necessarily highly accurate, right? I mean, so there is probably a high probability that some of them at least are going to be wrong. So you don't want to work with those labels, but at least it's giving you some information, right? So next pass is like, now that you have those synthetic labels, you have metadata on the remaining of the data to actually make a decision what kind of data you want to go with next. And so the typical querying strategy that people are going to use there would be something like confidence level, right? I mean, so for instance, maybe I want to label only the data that comes with a really low confidence from my preliminary predictions, right? And so basically the statement you're making here is like, if my confidence level is low, probably my model didn't understand. And so if the model didn't understand it properly, you can say, look, this is really an image that I think the model would benefit to learn from. And this is basically the logic behind active learning, right? So now that you have this data, you're going to select this specific data that you believe the model needs to learn from, and you're going to send this data back to be labeled by your oracle. And then this oracle is going to give you some information about, like, I mean, it's going to give you like the actual labels, right? I mean, the natural labels. And so this is really important to understand active learning, because if you look at my data over there, one of the images I actually believe, like the second was a cat. It's actually a dog, right? I mean, so because you inquired a label from the oracle, you're actually overriding the wrong decision that the model made, because again, if those were images with a low confidence level for the predictions, then there is a high likelihood that some of it is going to be wrong, right? So now you have the right labels. Hopefully your oracle is giving you the right predictions, and then you keep going like this, right? I mean, so you're going to add this data back into the model. You're also going to reuse the data that was already trained before. So now you have a little bit more data than you did at the first pass, and so hopefully this is going to increase the accuracy of your model, and now you have a little bit more data, labeling data to work with. And so as you go, like, you're hoping that you can see how the accuracy of your model is improving, and so you can decide to stop whether when your accuracy is high enough, whether or when you either run out of time, out of budget, or you have some kind of other restriction that forces you to stop the process. So you're actually being smart about like how much data you are throwing into the system and into the model. So how does this work intuitively, right? I mean, so basically, like, just imagine like you have this two-dimensional data over there that's like in the left corner over there, and you're trying to feed some kind of linear regression on top of that. Now assume I have a slightly different data set that has a little bit more data actually like spread all over the place. As you can see, you don't have as many data points on the corner, on the top right corner. And you see that there is a slight difference between the two predicted curves, right? So basically what's happening here is like the reason why I'm showing you these two different sets is like assume that if you were to randomly sample from this data here, it's very likely that you would probably get most of the data, if not all of it, coming from the bottom left corner, right? And so this shows you an example where doing random sampling would actually get you the wrong answer, because the important data here is actually spread everywhere, right? I mean, so there is actually more value and more information in the data that lives on the right. And so if you're actually missing this data because these data points come up more rarely, you're actually missing an opportunity to have a more accurate linear regression being fit onto the data. So basically the point here is like if you want to reduce the amount of data you're going to use to train your model, and if you just use random sampling, you might be failing because you're not being smart about identifying where the data lies and the value lies into your training set. So basically what's important here is like to understand that not all rows, not all data rows are actually equally valuable for your models to learn from. So quality is important, and the way it's being spread in the feature space is actually kind of important. And so the notion of its importance here is like kind of interesting because it actually depends on the task. And so that's why you want to use active learning, because active learning actually provides you the ability of injecting the knowledge of what you're trying to achieve here. Trying to identify value for a data set in a vacuum is actually very, very complicated because some data can be highly predictive of for some specific tasks, but not so predictive for some other tasks. All right, so now that we've gone through pooling active learning, I just would like to dig deeper and like discuss a little bit like the different like approaches we have, and also the different questions and challenges I hear from people to that extent, right? I mean, so what we just explained before was like something called pooling active learning. There is also another approach which is called streaming. So streaming gives you the opportunity to avoid like retraining the model progressively, right? I mean, so what you've seen before is like obviously one of the limitations is that you're retraining your model multiple times, which means that you're going to have an incurred cost compute-wise, right? So streaming is like really nice when you're working with streaming data, obviously, and so basically you're trying to make a decision whether you're going to use a specific data row on a row-by-row basis as your data comes in, right? I mean, so the challenges you're going to have there is like, I mean, the pros obviously is that it's more lightweight and you don't need to retrain your model consistently, and it works very nicely with online algorithms. The problem though is like you have no guarantee what your budget is going to be, right? I mean, so if your criteria to decide whether you're going to use a specific data point in your training set, and if you're going to have that data point labeled, if you use the wrong criteria, you might land in a situation where at the end of the day you're still gonna label 95% of your data, and obviously it's not really helpful for you. So the other approach is what we mentioned before, is like it's called pooling. So it's like exactly what we described before. So here, what's really nice about this approach is like your budget can actually be guaranteed, right? Because you can decide how much data, how much more data you're going to add at every step of your active learning strategy. And you can do real optimization because you're not just deciding yes or no, I want to use this specific data. You're actually trying to identify what is the best data for your model to work from at every single step. All right, so just like discussing like really quickly about different like active learning strategies. So there are really different buckets of active learning strategies. So the best known one is called uncertainty sampling. So uncertainty sampling is like at every step of at every loop within your active learning process, you're going to try and identify how uncertain the model is about some specific data points on which you try to run an inference, right? And so you can do that using confidence level. You can use that using margin sampling. Margin sampling is basically trying to identify how different is the confidence level between the first prediction and the second prediction. For instance, if your model predicts this specific image represents a cat with like a 40% probability, and then a dog with like a 38% probability, obviously the margin is not really high, and so basically that gives you an indication that your model is confused. Then you can use other things like entropy. I'm not going to dig into the details, but that's basically like the group of different strategies that consistently try to identify how wrong or how confused your model is. Then there is another like pretty well-known like type of strategy called query by committee. So query by committee is basically based on the notion of like ensemble techniques, right? I mean, so instead of having just one model, you actually use a group of models, and then you try to identify how many of those models agreed with each other. So if I'm, for example, using 5 different models at every single step, then I'm going to try and identify that the rows for which all models are in agreement with each other probably I don't need to label this data point because it seems reasonable to believe that the models cannot be all wrong, right? And then if you have other data points that actually have like 3 models that say this is a cat and 2 other models that say that this is a dog, look what, I'm actually going to ask for a human to have a look at this because I don't trust my models. And then you have lots of like more advanced like kind of situations like expected model change, generally speaking. So basically the strategy here is to try to identify how much knowledge you would gain by having information for a specific data point. And so this is the most computationally heavy active learning strategy of all. So discussing like active learning in general, right? I mean, so the reason why active learning is difficult to use is that you have to do a lot of what I call hyperparameter tuning for active learning. Active learning is just like deep learning. It's hard to decide the different parameters you're going to work with, right? I mean, it's hard to decide like should you be using a pooling, streaming, or synthetic query generation. Synthetic query generation being the third type of active learning strategy, where you actually like synthetically generate data that you believe lives in an interesting part of the feature space. What type of querying strategy do you want to use, right? I mean, so you've seen the main groups that I just shared before, but there are actually so many different variations of querying strategies. Even once you decide the querying strategy, you have to decide the pool size, right? I mean, so if you're using a pooling strategy, you also want to identify how many more data points do I want to add at every single loop within my active learning. And then you're also going to have to decide how many loops. You're going to have to decide the stopping criteria. And so that's a lot of decisions to make, right? And so there is currently no framework or no theory on how to make those decisions. So we're literally in the same situation that we are with deep learning, where it's a lot of trial and error. And if you actually get out there and try to read a couple of papers about active learning, you will see that this is exactly what people do. People try, test a specific querying strategy and just see whether it works for the specific use case. And so eventually, I think as the field becomes more mature, we're going to start gaining some knowledge around like which querying strategy is more appropriate for specific industries or specific use cases. All right, so I just would like to go through misconceptions within the active learning space, right? I mean, so the first myth that I hear a lot is like active learning is a type of model. Active learning is definitely not a type of model. It's actually a strategy. It is a wrapper around a model. So this is really exciting news because it actually means that you can use active learning in conjunction with whatever model you're already using today. And so basically, this is really cool. And so if you're in the situation where you basically thought you did not want to use active learning because active learning would force you to drop your current model, this is not the case. You can actually use active learning in conjunction with whatever it is that you're using today. All right, so the second misconception I hear a lot is like a querying strategy is a mathematical formula, right? And so it's actually not the case because a querying strategy is actually a dynamic sampling algorithm, right? I mean, so basically it does not need to be deterministic and it does not need to be based on confidence, right? I mean, so one of the things that every single time I discuss active learning with people, it seems like the querying strategy has to default back to confidence. It's obviously the most straightforward one, but it's definitely not the only one, right? I mean, so I'll just share a quick example with you here, right? I mean, so one of the reasons why I'm not a big fan of using confidence level is that if you look at the distribution of confidence level at the end of, one of your loops, right? I mean, so you'll probably, if you decide to actually go with like the low confidence level data points, you're actually very likely to select spam, right? I mean, so think about like your data being tweets, and you're trying to predict, like, let's say, like the language or like the topic of a specific tweet. Then the lowest confidence is probably going to come from the most spammy tweets of all. And guess what? If you actually keep selecting the spams as being the data you want to add to your training set, you're actually polluting your data set. So how do you deal with that? You can do something that's actually a little bit smarter, and you can decide that you're not going to take the ones that have the lowest confidence. You're going to take the ones that are some medium confidence out there, and then you can do some random sampling over that to like make sure you're not biasing your existing training set, and then you can try to like counterbalance like the lowest confidence with like the highest confidence within this medium confidence bucket over there. And then the third myth that I've heard about a lot is basically like you still need to use all of the data to get to the highest accuracy, right? I mean, so at the end of the day, if the goal of your company is like to reach like the 95%, 97% kind of accuracies, you're still going to have to use all of your data. And this is where actually active learning becomes interesting, because when you do active learning, you're actually in the business of trying to identify the rows that are actually potentially hurtful to your model. So again, the spammy things, like the images that have sun glare in them and so forth and so on. And so sometimes when you're doing active learning, you can actually reach higher accuracies than you would by throwing all of the data, just simply because you're removing this data, the data that might be harmful for your procedure, right? So let's discuss really quickly like the different challenges here. So again, there is no theoretical framework on how to do hyperparameter tuning for active learning. There is no guarantee about compression rate. I mean, so it's impossible, or right now there is no framework to basically predict that if you use this querying strategy, you're going to be able to reduce the amount of data that you need to train a model by a factor of 50%, for instance, right? There is obviously a trade-off between cost of labeling and compute power that you're going to have to consider if you're using pooling active learning. And so sometimes active learning doesn't even work at all. So I mean, if you look at all the surveys of like different papers, there is actually like about 10% of researchers that say that after they use active learning, they actually got worse results than without using it. How is that possible? It's possible because sometimes you're just like getting the model confused by identifying the wrong initial training set when you start the entire procedure. And so getting the right initial sample and being smart about how you identify your initial training set is actually really important. And so there's like, at the end of the day, the way we're going to solve this is like by having more and more people use active learning and like started building theories around this. But there is really a sparsity of use in some use cases, right? In some specific domains, like people haven't even started to think about using active learning, and so it's difficult to like come up with the best strategy in these cases. So conclusion here, right? I mean, so we've seen that like good data is really instrumental for machine learning, so it's good news because we're now at a stage where it becomes possible for us to be picky about the data that we select. And so, but unfortunately, a lot of the data comes unstructured and it comes unlabeled. So you still have to process your data before you can use that for your machine learning applications. You do need labeled data if you want to do supervised learning. So even though you have a lot of data, don't get excited too quickly because you still need this data to get processed and prepared. We are now seeing like a shift of like a challenge moving from like data collection to data labeling. So like we have a big data labeling crisis today. And so it's all about like labeling faster and or labeling smarter. And so this is how Figure 8 can help. And then finally, like so active learning like definitely can help you dramatically reduce the cost while improving accuracy. It is definitely an opportunity to enhance your models, and so it's going to make your models even better if you do it the right way. It is a strategy and an algorithm, not a model, so you can really combine this with whatever it is that you're doing today. But unfortunately, it can be hard. So, all right, thank you so much for your attention today. And so I will go back, I'll get back to you, Bill, I think. So you have to step in.
Right, Jennifer. Oh, thank you so much for that really excellent presentation. And we'll get started with today's Q&A session. And I want to thank the audience for their participation. We had a lot of questions that have come in, and we'll do our best to get through all of them in the time remaining. And so during this Q&A session, I'll leave up this screen with contact information for Jennifer in case you'd like to get a hold of her following today's webinar. So let's get started. Jennifer, can you start by just giving us a couple of real-world examples of companies that are using active learning and in what capacity they're using active learning?
Yeah, absolutely. So I think I see like maybe like probably like two major cases in which like active learning is becoming really popular. So like the first one is like obviously like autonomous driving, because again you have a lot of data, but you also have a lot of like problematic data, again like sun glare images, or like a lot of data that people know that will actually hurt the model if you throw that into your model. So the fact that you're using active learning is actually help you trim down the huge data set that you're dealing with by removing the data that would be hurtful to your model, right? I mean, so there is not only the opportunity of reducing the amount of data you need to train the model, but also to identify the data that would be problematic. And then the other use case that I see a lot is also related to like use cases, specifically NLP use cases, like document analysis and so forth and so on, specifically for legal companies, where it is problematic to have all of the data labeled just because it's really expensive, because you need to spend a lot of time as a contributor or as an annotator to go through all the documents. So it's really about like trying to reduce dramatically the amount of data that you need to get labeled. And so that's I see that a lot in the context of NLP.
Well, thank you for those examples. And by the way, one of the things you mentioned was eliminating data that might be bad for our model, and that ties very closely to the audience question about, well, doesn't this learning curve, active learning, create sample bias? But maybe in this case, good sample bias.
Yeah, exactly. So that's actually a very common question I get. Like basically, a lot of people assume that you will be easily in an overfitting situation if you actually use active learning. And so I will actually claim that active learning does quite the opposite, because it's actually enforcing diversity within your training set. So let me explain why. So simple case where you're trying to use images to predict the animal that you see on that image, right? If my training set has a lot of data that actually shows cats in front of red backgrounds, right? I mean, so overfitting would basically be the case that the model assumes that whenever you see an animal in front of a red background, it has to be a cat, right? So guess what? If you actually like use the simple use case where you use confidence level as your querying strategy, then you will quickly land in a situation where the model is fooling itself into believing that cats and red backgrounds are associated, right? And so the next time you're going to do inference on the remainder of your training set, the unlabeled part of the training set, right, you would actually have a very high confidence that images with the red backgrounds are cats. And then you will stop querying these, right? Because again, you have a high confidence for these predictions, and there is no reason why you would keep adding these type of images into your model, right? So what's going to happen next is you're actually going to start selecting like data that is from the rest of the data set, the part that's not a red background, right? So you're actually actively contributing and enforcing that your sampling strategy is going to go after the images that are different from the ones you already learned from. And so as you go, you're actually going to help your model unbias itself and avoid overfitting.
That's a great example. I like that a lot. In your presentation, it looked like a lot of determining how many times to use active learning was just kind of a stochastic ad hoc procedure. Is there any guidance you can offer on how to judge when you've reached an optimal point for active learning?
I mean, the secret is really like focusing on the learning curve, right? I mean, so basically, like unfortunately, the learning curve that I showed in my example is like the smooth case, and we all know that sometimes you're going. I mean, it's just like as when you train your regular models, sometimes adding more data is going to drop a little bit the accuracy of your model because again, it's stochastic, right? I mean, so there is no guarantee of that. So I mean, it's just like really exactly the same kind of situation. Then how do you know that you're in a case of overfitting with deep learning, right? I mean, so you have to like start looking at the different metrics that you use to train your model, and so at some point you're going to identify that you reach the same point. So I think it's really exactly the same thing that you would do when you're doing hyperparameter tuning with your deep learning models.
Indeed. Okay, understand completely. You know, we talked about a lot of examples that had to do with classification. Is active learning something that can also be used for regression type problems?
Yeah, absolutely. So it can absolutely be used for that. I mean, there's absolutely no, like, I mean, you have all the elements in regression that you have for classification, right? I mean, you still have a confidence level with your prediction. You still have like a to do some labeling and so forth and so on. Like, for instance, like I see a very sweet spot for doing active learning in combination with a predicting bounding box on an image, right? But I think the reason why we don't see a lot of these use cases on the market yet is like we're still in this discovery mode where classification seems more straightforward and more, I would say, intuitive for people. So there are definitely more and more cases that I see that lend themselves very nicely for active learning that use regression, but it's still a very sparse pool of different use cases. So even if you try to look into like use cases in academical papers, you don't see that many examples, but there is no reason why you wouldn't be able to use that for regression.
Makes perfect sense. Thank you for that answer. And the other type of problem that we frequently run into are training sets with really very highly imbalanced sets. Is there some special guidance for handling highly imbalanced sets with active learning?
Yeah. So that's actually that's probably one of the biggest problems that I think like needs to be resolved in the near future, because like I would say if you get it, like the biggest problem is going to get your initial training sample, because again at this point you have absolutely zero guidance to know what your distribution in terms of the different classes you're looking at is going to look like, right? I mean, so basically like there is no way to do stratified sampling, for instance, if you don't have the labels and you don't have knowledge of what the different classes are, right? I mean, so it's all about like being smart about how you do your initial training set. So if you're in a situation where you really believe that there is a high likelihood that you're going to have a huge imbalance, I would say that my best suggestion would be generous with the size of your first training set, right? I mean, your initial training set, like your initial data sample. As we go, I think there is an opportunity to use the same techniques that we use for like doing sampling in the context of reinforcement learning to actually be smart about the data we select, right? I mean, so looking at, you know, like the distribution of your data, like across the feature space, like doing some kind of clustering analysis before you get started usually gets you some indication of like how your data is being distributed across the feature space. So I think adding this additional phase where you try to get an understanding that like there are that many different clusters within your data, even if you don't necessarily know what your clusters are. I mean, it's actually a smart way to be smart about the way you start.
Oh, thank you. Thanks for that explanation. Makes perfect sense. Now, I think I understood, and though it left a little confusion for some members of the audience, you know, in each iteration of active learning, did that always involve first a machine learning oracle and then a human oracle?
No, absolutely not. No.
Okay.
No, so basically, like the concept of oracle is really the agent that provides the label, right? I mean, so you really have two different ways of thinking about this. Either you just ask a human, or you ask a separate machine learning model. So I just want to make it clear that this machine learning model is a separate model from the model you're using to in conjunction with active learning, right? I mean, so it would be like maybe a YOLO algorithm that's trying to predict bounding boxes somewhere, right? And so the oracle is like literally just the agent that provides the label, right? So just like building on top of what you just asked, Bill. So I think it's really important to understand that active learning is really a nice and important like part of semi-supervised learning, because semi-supervised learning has been known to generate biases, and that's the reason why it's been really unpopular in data science. And so the reason why like active learning is actually pretty safe is that at no point in time you are using synthetic labels. You are using synthetic labels to identify what data you want to get labeled, but the labels you actually use within your training sample, right? I mean, so basically like the data you're going to use to train your model is always labeled by an oracle, right? I mean, so you are not playing with like predictions that might be wrong and that we know are probably going to be, at least with some probability, going to be wrong because you used an algorithm that's not very accurate when you get started with your active learning.
Well, okay. Then in that case, if the oracle is human, what's your experience with the accuracy of scoring by human oracles? Is it always accurate, or do I have to allow for some inaccuracy even with human intervention?
Yeah, so that's a good question, and I think it's a problem you have not just for active learning. It's really a problem you have for data labeling in general. So even though you decide not to use active learning, it's still a problem you're going to have to face, right? Because at some point the question comes down like, how do I actually make sure that the answer I got from my my human labeler or my human annotator is actually correct? And so, fortunately, actually, Figure 8 actually has like very nice accuracy control in place that allow you to get a strong measurement of how accurate your labeling process is. And we're also in the business of like identifying who are the bad actors on the platform, right? I mean, and so basically we try to make sure that the person that actually provides the label is actually doing their job properly.
How about that? Well, Jennifer, thank you. Those were some great answers to some very good questions. And for those of you that asked questions that weren't answered today, we'll be sending all the unanswered questions to Jennifer and the Figure 8 team so they can follow up with you after today's webinar. You know, I have just a few quick announcements. If you'd please mark your calendars for December 11th, that's our next DSC webinar, which will be Connected Intelligence Solutions with AI and ML. Also, remember that today's taping will be available for on-demand viewing later today, and you can find that on the home page of Data Science Central in the Webinar tab located at the top of the page. Also, you know, past webinars are available on demand at datasciencecentral.com, and if you haven't had the opportunity to take a look, I encourage you to check into that. They provide very useful insight into a wide variety of topics of interest to our data science community. Well, this brings today's webinar to a close. I'd like to thank our audience for their attendance and thoughtful questions. A special thanks to Figure 8 for their sponsorship, and particularly our speaker today, Jennifer Prendke, for her insight into today's topic. So this is Bill Voorhees. I'm very pleased to have been your host for today's event. I look forward to seeing you all again on December 11th. Have a great day.